Hi guys, my name is Franz, and in this video I'm gonna prove that the language we saw in the previous video is not regular by using the pumping lemma for regular languages. Okay? This was the language we saw in the previous video, the language L, 0 to k, 1 to the k, where k is greater or equal to 0. Now, as I said in the first video of the pumping lemma for regular languages, we always follow the same steps, the same process, right? You take a language L, which is not regular. Then you suppose that L is regular. And remember, this is a hypothetical situation because L is not regular. We know that already. We saw it in the previous video. Now, to make my point, I'm going to start talking in a hypothetical way, okay? If L were regular, then there will be a variable P, which in practice is the number of states. And P is called the pumping length. But in reality, there is no P. P doesn't even exist. And that's because L is not regular. And that means that there is no DFA. There is no number of states. And there is no P, right? Okay. Now, if there were a variable P, then there will be a string W, which would be at least as large as P, right? Now, the string W could be written in terms of XYZ, right? And once you have W equals to XYZ, there will be three conditions that you guys already know if you saw my first video. Y is never empty, the length of XY is at most P, and the pumping condition. Then you apply the third condition, the pumping condition, and you get a contradiction, always. And you conclude that L is not regular by contradiction, and you are done. Fair enough? Okay, we said that P doesn't exist. There is not a concrete value for P, because this is a hypothetical situation. Now, the question is, how do we choose the string W, which has to be at least P, if P doesn't even exist, right? I mean, if we don't know P, how do we choose W and make it at least P? That's the real question. Well, the only way to choose the string W, which is at least P, is by choosing a string W that is in function of P. The string W is always in function of P, always. Now, in this example, we just have one choice for the string W, which is this one. And this string is in function of P, as you can see. And we choose this string because this string is in the language. What's the language again? The same number of zeros followed by the same number of ones, right? Here we have P zeros followed by P ones. So this string is in the language. And also, this string satisfies this condition. Because what's the length of W? The length of W is 2P, which is at least P, right? And once we have this condition satisfied, and we have a string which is in the language, the pumping law for regular languages applies. Okay, let's write W in terms of XYZ. And this means that 0 to the P, 1 to the P is equal to XYZ. Now let's keep in mind the second condition, which is the length of XY is at most P, right? Now, what does the string look like? What does this string look like if the length of XY is at most P? Well, this is what the string looks like. We know that the xy is located in the first p characters because the length of xy is at most p. It couldn't be here. It couldn't, because we would break this condition, the second condition. And also, we have no idea how big the x and y part are. We don't know how big they are, because again, this is a hypothetical situation, okay? So xy consists of zeros in this case. Now, let's use this condition, the first condition. Y is never empty. It means that the y part must have at least one zero in this case. And at the same time, y is at most p because of the second condition. So there is a range, there is an interval for the y part, okay? Now, to generalize this idea, I'm gonna make the y part consist of alpha zeros, okay? Y is equal to alpha zeros now, where alpha is between 1 and p. And also, alpha is an integer, okay? And of course, we don't know alpha. We don't know the value of alpha. And we don't need to know it, because again, this is a hypothetical situation, right? All we know is that alpha is between 1 and p, or in other words, the y part contains at least one zero, and at most p zeros. The y part contains alpha zeros, right? Now, let's apply the third condition, the pumping condition, and see what happens. So, the xy part is somewhere in the first p characters, right? Like this. Now, what happens when you pump up? Well, when you pump up, you're adding an extra y. And y contains alpha zeros, remember. And this string is not longer in the language, because the language is the same number of zeros followed by the same number of ones. But here, you're adding an extra y, and now you have more zeros than ones. So we rate the quality we had before pumping, right? Now, to make it more clear, this string is equal to this. 0 to the p plus alpha, 1 to the p, right? And here you can see that p plus alpha is greater than p, and we break this equality, right? Now, you might want to pump down and see what happens. Then you subtract the y part, and the y part becomes empty. Y becomes empty. And in this case, p minus alpha is less than p. And you break the equality again. So you get a contradiction in both cases, because the pumping lemma for regular languages says that I can pump up or pump down and stay in the language, which is not the case. Therefore, our assumption that the language L is regular is incorrect, and the language is not recognizable, you can say. Now, there will be some examples where you only pump up or pump down. In this example, we can do both, right? Alright, that's it for this video. I hope this was clear. So thanks for watching, and see you next time.